here's my cartoon of what I think happens in this problem. In the first picture, the spring is compressed some distance x that they tell you, and the mass is sitting in front of it. In the second part of the picture, the second scenario, the spring has fully released and is just dangling there, and now the box is moving pretty fast because there's no friction here. In the third part of the problem, this is the frictionless surface that used to be there, but now the box has gone onto a place where there is friction. So there's the rough surface, and there's friction, and they tell you about the coefficient of friction. And in the ending part of the problem, the box finally stops. So they want to know the distance that it moves across here. So they want to know the distance. So what I do is I think about what's happening in each of these pictures. So in this picture, there isn't any gravitational potential energy because it's not going to fall, but there is potential energy because of the spring. So I'm going to write that here we have 1/2 kx squared. There's no kinetic energy, translational or rotation, so I'm not going to put anything for kinetic energy. So that's a total of what's going on in that picture. In the next picture, there's now no gravitational potential energy because it can't fall. There's no longer any spring potential energy because the spring is now slack. So the only kind of energy we have here is kinetic. And the only type of kinetic energy is translational. So here we have 1/2 mv squared. Now, during this next picture, what's happening between here and here is that work is being done, right? So the friction is slowing down the block, taking away its kinetic energy. So what's happening here is work. And work is always equal to F d cosine theta. And the force is friction. And friction is mu times the normal force. And if we have a look at that free body diagram, we've got mg pointing downward, we've got normal force pointing upward, and friction pointing backwards. And we see that n minus mg has to be equal to 0, so that means the normal force equals mg, and so the friction is mu mg. The distance for the work equation is the question that they're asking. What is the distance that it travels while it slows down? So that's just going to be d. And then theta, we have to think about that. It's going this way. That's the displacement. And the friction is that way. So theta is 180, and the cosine of 180 is -1. So we put that all together, and we find out this work is equal to minus mu mg times the distance. Okay? Now, when we get to the end, the final picture, the total amount of energy here is 0. Because there's no potential energy anymore, no kinetic energy anymore, nothing's going on. So, what happened to all the energy? Well, it got taken away in work. We could write several equations here. We could say that 1/2 kx squared is equal to 1/2 mv squared. That's true. And those are also equal to the amount of energy that was lost because of the work. So that's also equal to mu mgd. I didn't use the minus sign here because we're talking about magnitudes now. So the amount of kinetic energy it has before is equal to the magnitude of the work. Or you could say that the work is equal to the change in kinetic energy. So if you want to call the work minus mu mgd, then that's going to be equal to the final kinetic energy minus the initial kinetic energy. The final kinetic energy is 0 minus 1/2 mv squared. So again, we're going to see that minus mu mgd is equal to minus 1/2 mv squared, but instead I said that they were both positive like this. So this equation tells us about everything that's happening in this picture, about the blue one is equal to the red one is equal to the green one. What we're trying to find here is D, so we want to choose an equation that we have a lot of information about, and we have a lot of information about the blue situation. So the equation I'm going to choose to solve is 1/2 kx squared equals mu mgd. And I think you know everything in that equation except the distance, and you could solve.